Thank you so much. Hi, everyone. I'm glad that you made it back after lunch. Some might not make it back, so thank you for being here. How many people know what this is? Anyone? Just raise your hand if you know. 2 people? 3-ish people? Can you throw a name that you think made the name of the person? No. This thing. It's a specific machine. Who made it? No. Oh, very close. Who said homeostat? Close, but no. Very close. Okay. Who knows what this is? Or what is the shape that this maze is portraying? Okay, good. We're in good company. Okay, so when we talk about reinforcement learning, I'd like to clarify that there are different meanings of it. And although they are connected, Erica would be talking a little bit more about the first one, which is a concept in animal studies. Usually it refers to using reward to shape animal behavior in specific tasks. Imagine pigeons. You feed pigeons a certain reward when they repeat a particular action. After a while, they get better at that task. The reward is usually something that they need for survival, and often they are kept hungry so that they actually want it. Food, water, etc. Exploration of complex, often nonlinear reward structures like pleasure and pain avoidance is kind of studied with this. But what I'm talking about today, and Erica will talk about the first kind, is in computational sciences, in which reinforcement learning is a framework which was formalized in the 80s by Sutton and Bartow, where an agent takes actions in an environment to maximize expected discounted rewards. We'll talk about all those things soon. And rewards are defined by some explicit scalar value usually. And it's usually simplistic and abstracted notions of rewards, like game points, or you get a 1 if you win Go, or if you have task completion. It's goal-oriented and efficiency-driven, and the whole point of it is maximizing cumulative reward. But we will talk a lot more about this. This is just like the beginning. So this is the SNARK machine that was made by Minsky, or some version of it. And it included 40 artificial neurons. It hopefully will become clear by middle of the talk why this machine is here. This is a photo that I took in a recent talk by Andy Bartow, one of the founders of reinforcement learning as a framework, whose talk title was, in the beginning, ML was RL. And what I would like to show also is that in the beginning, RL was philosophy. Let's take a quick tour of the historical or intellectual prehistory of RL and see where do RL equations come from. We will take a look at these equations during this talk, which address model-free, model-based RL, and also successor representation learning. We will talk about how we can use RL to study behavior, neural patterns, as well as build things that sound intelligent because they have learning and memory. But before that, let's start by taking a look at where the ideas or the equations of this RL and machine learning come from. And I want to invite you to, during the talk, imagine how things would be different, the equations would be different if another philosophical approach was the foundation of machine learning. And you don't need to throw it at me during the talk, but I would love to talk to you guys during the next 3 months about what other mathematical foundations of intelligence can come about if we consider other philosophical foundations. Okay, so I apologize, there's going to be a lot of text, but only for a certain amount of the talk, and then it's going to get a little bit more fun. So Jeremy Bentham is the kind of theorist of hedonism, and he suggested that nature has placed mankind under the governance of 2 sovereign masters, pain and pleasure. This idea was also closely related to the principle of utility as a measurement of how any individual and government action augments or diminishes happiness. And Bentham proposed a way to quantify this measurement. This is what he called the hedonistic calculus. Now, later on in the 1850s, we have the Spencer-Bain principle that says the frequency or probability of a behavior rises if followed by a pleasurable event. If you guys know reinforcement learning, you will see how this is completely the foundation of all of it in some ways. Decreases if it is followed by a painful event. You will also see how this is the hedonistic principle of synapses in neurons and how that led to a lot of the sort of work that is in machine learning today. Now, the Spencer-Bain principle connected the philosophical tradition of utilitarianism and British associationism to psychological theories of the late 19th century. That is the foundation of a lot of the work that we are doing. In the 1800s, the idea of learning as trial and error followed. Learning as a process of trial and error was also proposed by Huxley, 1864, that drew on Darwinian evolutionism. So if you see similarities between Darwinian evolutionism and learning, it's because they were literally coming from the same philosophical principles. For Huxley, the origin of species showed that perceived intelligence in organisms' apparatus serving a certain purpose should be explained as a result of a grape shot, like hit something and the rest will fall wide. Trial and error, in other words, was the way unintelligent organisms gained the appearance of intelligent behavior. So for the early kind of psychological sciences, all intelligence can kind of boil down to very simple conditioning. We no longer think that's the case, but that was the kind of the ideas of the time. This idea of intelligence as unintelligence, explaining intelligence by boiling it down to trial and error and conditioning, is also represented in Jacques Loeb's idea, who was, I think, one of the, at least in the 19th century, one of the main people who claimed living organisms are machines. So this is before we have machine learning, right? And we need this kind of thinking to be able to abstract. But just like the Wittgensteinian ladder, once we use a ladder to get to the rooftop, we can throw it. We don't need to think the way that 19th or 18th century people thought about it anymore. Then we had Morgan, who proposed a canon by 1900s, well, exactly 1900, as a methodological guidance for studying the mental evolution of faculties starting from the lowest kind. They had an imperative. This canon said one should always use the lowest explanation for animal behaviors, a reductive understanding of animal and later human behaviors. And if you look at the Marvin Minsky's Society of Minds, it's exactly based on the same idea, that you have dumb pieces that together build an architecture of intelligence. I personally was completely under this assumptions 20 years ago when I entered as a kind of a wide-eyed undergrad. But I think now I come to think that even a single cell is more intelligent than GPT-4, and hopefully within this talk and the 3 months we can talk about these things. Now, Morgan's canon explains intelligence with unintelligence. It lowers the bar for intelligence under trial and error, and that's the algorithm we have. Initially, it's just a mathematical method, but gradually becomes generalized in the nature of learning in experiments in the 19th century. By 1920s, it is accepted in psychology that much human as well as animal learning proceeds in the method of trial and error, which we now know is not exactly very efficient. Now, this downgrading of intelligence that is done by Watson and Loeb suggests that behaviors of higher faculties can be shown as much simpler reactions for Loeb and reflexive reactions for Watson. As you know, Watson is one of the fathers of behaviorism, which we'll talk about very briefly also. Loeb calls elemental reactions automatic mechanisms. So this is where this term actually comes from translating philosophical principles of utilitarianism and trial and error into understanding of intelligence as accumulation of unintelligent pieces or behavior or associations. Now, the foundational conceptualization of intelligence by early behaviorism and J.B. Watson is that all human behavior is conditioning. So we are all Pavlov's dogs. Then we have Thorndike's law of effect, 1920s, who translated the underlying hedonist principle and made it the general principle for investigating animal behaviors. Thorndike's law of effect was described as psychological hedonism in the 1920s. The idea was very simple. You know, I don't know why there's so much of early 20th century science relying on cats in boxes, but such is life. So this cat is in a box. If it pulls a lever, it can get out of the box. And the whole concept is if it gets reinforced by cat food when it gets out, it's just going to do that faster or better. And just the very simple ideas of cats in boxes are really the foundations of so much of machine learning. Now, let's take a look at classic behaviorism that emerges at the time. First, it denies internal life. It says it's all about reinforcing certain behaviors. There's nothing inside that matters. Obviously, we don't think so anymore. It emerged as the dominant research paradigm in animal psychology in late 19th, early 20th. Radical forms are associated with Watson and Skinner, which share a lot of core ideas. And to claim the status of science, at the time, it was really uncool to think about feelings or thoughts or internal states or mental states. So in order to achieve the status of science, behaviorism denies the relevance, if not the existence, of mental entities, such as consciousness and concepts such as purpose. Behaviorism maintains that all behavior is generated in response to reinforcement by the environment, excluding internal life. Behaviorism adopts as a methodology that supposedly only derives conclusions from observable behavior. And that's how you gain the status of science, obviously, at the time. Now, I'm not completely bashing any kind of outcomes that came throughout the years from behaviorism. But we can see, I don't know how many people still would think this way, but we can see that it's a very extreme way of looking at behavior and mind. Second, behaviorism claims that the environment is the source of behavior. So rather than internal factors, behaviorism treats external or environmental factors as the sources of behavior. Through observing the control exerted by the environment, Skinner wrote, we can examine the effect of the world within the skin. So forget about inside the head, look outside. And more importantly, behaviorism was a science of control. I don't have time to go into the details of that, but there's a lot of ties to unfortunate colonialism and racism as well in it. Watson declared behaviorism as a science of control, the goal of which is the prediction and control of behavior rather than understanding, which is at least the goal of some of us who are interested in natural sciences. For Watson, all human behavior was conditioning. And as you know, there's Pavlov's dogs. You ring a bell before you give them a food. Then the bell itself, which is an unconditioned stimulus, starts to lead to salivation after a while because associated with what will follow next. And here you see that the dog says, watch me every time I salivate. This guy starts to write something there, so it's kind of reversing. Now, later, Skinner generalized his thesis to contend the inevitability of the socio-cultural shaping or conditioning of human behavior, which implies that we cannot choose a way of life, but we can change the controlling conditions with the help of behaviorism. So you see, the ideas, the work is very philosophically and ideologically driven. When we think about understanding nature or studying nature, I think it's important to study where our methods come from. How will they be different if another philosophical or ideological history was the beginning or the initiation of them? Another interesting thing is any political philosophy that you will read starts off with some assumptions about the mind. And you can see the ways in which we will think about how the mind works. What are the models of mind? What are the mathematics of intelligence? Actually says something or bears some influence on how we think humans should be governed, treated, etc. So think about those consequences as well, especially since I know some of you work on policy. The work that we do here doesn't just have importance for making neural networks. It actually has importance for the ways we think. Yes? Prediction and control. Control is understanding. I would say if you want to let's talk about ecology, or let's talk about nature. If I want to understand nature, maybe the idea of control as just experimenting a little bit would make sense, but the idea of control as I want to control nature as a whole for my own purposes, that's not a part of it. So that extra part, which is at the level of a sociocultural even program, is something that is core to behaviorism and its earlier predecessors, which is not the program of natural science. Dominating nature is not the program of natural science. Understanding it is. Minimally using control to do experiment is, but controlling overall society and nature is not. Yeah. Again, doing small experiments with minimal amounts of control is different from exercising control over society. Okay. Anybody? Yeah. Ooh. Amazing. I'll definitely take a look. All right. So now let's come to what happens when we take all these philosophies and ideologies, simplifications, and put them into some transistors. Minsky's go-to learning model was B.F. Skinner's operant reinforcement, in fact. And he used the term reward to generalize both positive and negative reinforcement. And here you can see the sort of machine he made that was called SNARK. And it has 40 artificial neurons, and one of them is in this picture, which were interconnected with a plug board and held in racks in a contraption about the size of a grand piano. So this is just like a piece of it. At one end of the neuron was, I'm not going to go into detail because I'm realizing I need to look at the time, but definitely Google it. It's very interesting. And then on the right, you can see Wallace's maze solver. And then you have psychic machines. There is this whole era of cybernetics. You see all these very cute little machines that are running around. Roomba is the grandchild of one of those. It's a very interesting time where suddenly simplifying things using this philosophy of utilitarianism allows for building things. So although perhaps behaviorism was not necessarily the best approach for understanding nature, it was certainly helpful in engineering tiny little robots and intelligent machines, or some simplified notion of intelligence. And I do distinguish engineering and science, and their goals are different, obviously. Control is one of the kind of interests of engineering versus science, by the way. Okay, let's go back to a slide or a similar slide to what Mayank showed earlier. This is obviously a synapse, and as we talked about a little bit during that time, it has a bunch of different things in it that happens in order to transfer some information and gather certain evidence to strengthen or weaken certain associations. You probably, based on everything that we said already, might guess how a synapse is hypothesized to increase or decrease some weights or efficiencies based on getting rewarded or punished, obviously. And someone asked about the earliest kind of entity we know with neurons. This is Hydra, one of our evolutionary ancestors. Does not have a brain, but has neurons. And also is kind of a very interesting creature if you want to read about it online and look at different diagrams of it. And there are very many interesting drawings of it by various people as well. So without further ado, I put here the talk of Andy Bartos, so I make it very clear how much influence from these kind of prehistory of machine learning from neuroscience is very widely acknowledged by the founders of reinforcement learning. So we have Klopf in the 1970s with the hedonic neuron hypothesis, who says neurons are individually hedonistic. They work to maximize a local analog of pleasure while minimizing a local analog of pain. In the famous book, The Hedonistic Neuron, is something you can take a look at. The simple idea is that this is the synapse we talked about. You have basically action potential, and when the action potential happens, the synaptic efficacy becomes eligible for change. And that's it. That's the notion of eligibility. So if it's reinforced, increase the efficacy. If it's not, then reduce it. Klopf's hypothesis that synaptic plasticity, and this is the notion, this is all that plasticity really means, right? So it becomes eligible for change under certain conditions. Therefore, it allows for plasticity in this case. So synaptic plasticity implements a law of effect. Remember Thorndike. So that's again coming back here. When a neuron, by the way, Thorndike was extremely intelligent. If you look at the academic trajectory, even from undergrad, extremely impressive work. When a neuron fires an action potential, all the synapses that were active in contributing to action potential become eligible to undergo change in their efficacies. If the action potential is followed within an appropriate time period, and that's key, we will see why that matters, by an increase in reward, the efficacies of all eligible synapses increase or decrease in the case of punishment. Klopp's idea was changes in membrane potential, but they also explored temporal difference error delivered to the neuron. So we will get to what temporal difference is. So you see again, Andy Barto acknowledging learning by trial and error and instrumental or operant conditioning. You can see how much the foundations of reinforcement learning and machine learning are completely inspired by the work I mentioned. So the birth of modern reinforcement learning, although the term first appears in Minsky's thesis, the birth of reinforcement learning in a formal way is in 1981 with the paper that was published in no other than Psychological Review. In fact, Rich Sutton did his undergrad in psychology, and a month ago he told me that he thinks that his secret weapon is actually studying psychology and neuroscience even until today when he wants to find new ideas. Sutton and Barto really formalized a mathematical system that can be used for many different kinds of learning and is actually used in many applications that you know today. Something that Andy Barto beautifully mentioned is that, and I think perhaps Peter Todd would appreciate this as well, that basically reinforcement learning is just search plus memory. Search being different types of search that can happen, and as we know, there are a lot of more complex search algorithms that happen all the time. And then memory would be cache something that worked out so that you can use it later so you don't have to compute it from scratch. So this idea of caching and search is really at the foundation of all of the algorithms that you would see, plus minus other things. RL is about caching search results, so you don't have to keep searching. In other words, this is not a typo. There is a notion of memoized search, which you can look for it, and contextual search. All right, what time are we? Okay. So this is the very foundation of so much of RL that we know of. This is temporal difference learning of value. And the idea is that temporal difference gradually updates cached value for state S. So what you see here is V. V stands for value of S, which is a given state. Let's say this is the state you're in. What is the value of being in this state? The value of in this state is the value I've cached for it already. Let's say you start with a 0, plus some learning rate. You can ignore it. You can assume it's 1 right now, but we will talk about what it really is. Some reward that you observe, plus the discounted value of the next state that you're going to visit when you take a given action. Let's say when I take action A, I see reward R and go to S prime, minus the old value of S. This term is prediction error, and we will come back to it again. I will mention it again. And prediction error, yeah?
Is it supposed to be S prime on one side or the other of the equation?
S nu is the same as S prime.
But it's like a programming language sort of
Oh,
notation.
okay, got it.
You're updating these.
Okay.
You're updating value of, yeah. And you update it once I'm here, and when I arrive to IPAM, I end up going to a museum. And it's amazing. That's my S prime, this is my S. So the value of IPAM is the value I thought IPAM had, plus the prediction error I got, which was very positive that I went there. Now let's say the opposite happens. I come to IPAM, and then for some reason, I don't know, I'm pulled over and I go to jail. That would be a negative prediction error. And then the value of IPAM would kind of diminish because it's added that thing, right? This is temporal difference learning. And why is it temporal difference? Because it depends on different times that you go and visit this place. Gradually, it changes. This alpha is between 0 and 1. What do you think is the learning rate of humans between 0 and 1 on average in experiments? Throw a number. Throw some number.
0.1.
0.01.
How many people think it's lower than 0.5? How many people think it's higher than 0.5? How many people think it's lower than 0.2? Okay, it's between 0.2 and 0.5. So it's a very interesting distribution. It had a pessimistic tale about humans. Okay, so let's take, yeah.
What about gamma? What's
Oh, great, yes, great. Gamma is the squinting factor. So basically, because when I am here, I am not in the museum yet, I am not pulled over by a cop yet, therefore I discount a little bit the value of the next state. Now, if the gamma is very small, I'm a little bit more in the present. If the gamma gets very large, it means I'm looking very far away. Interestingly, and I hope I get to show you, if not in this lecture, then in the next one, that in fact we find that in the hippocampus and the prefrontal cortex of humans there is different gammas, or there's representations with different gammas. But this is model-free reinforcement learning. And for this one, even in the basal ganglia, you see different gammas. So if you want to do motor actions, like if I drop this and I want to catch it, this is a very fast gamma. But if I am thinking about when I'm going to get lunch, that's a little bit of a slower gamma, even though it can still be model-free. Yeah.
So when you say alpha for humans, like how can you possibly know what an alpha is for?
It's just based on experiments that you observe.
Best fit alpha. Or something.
Yeah, yeah. Obviously, there are many times we do one-shot learning. It's not that you don't have the other ones. Just on average, it's about that. Also, when you have more uncertainty, alpha goes down, because if there are things that are very unsure and you have a lot of prediction error, you don't want to overgeneralize too much. If you give me $1 every time you see me, that's a reliable thing. But if one time you give me $1, one time you ask me to give you $100, one time you give me $2, then that seems like, okay, maybe I can't update my prediction of you. So that's like the way in which I might need to lower my learning rate. Yeah.
Does it change with age?
It does.
Children have...
Absolutely. There is developmental effects of it, not just for alpha, also for gamma, also for so many different things. In general, when you get older, you don't want to have a very high alpha because you have probably learned something that helps you survive in the world. Okay, so if you guys went to SFN over the past 15, 20 years, and you took a shot every time you saw this slide, you might have an alcohol problem because this would appear in so many different neuroscience talks. In 1996, things went back the other way. So it was constantly from neuroscience and psychology into ML, and now it went back. Because Montague, Diane, and Szynovsky decided that they're going to test the idea of TD prediction error, and they found that it actually captures dopamines and dopamine functioning. And then it turns out that it's not just in mammals. In fact, the kind of another creature that was mentioned in Mayung's talk was C. elegans. And it turns out that C. elegans uses dopamine as neurotransmitter to regulate motor behavior and uses prediction error in learning. And in fact, there's a person who won the Nobel Prize for the study of memory in C. elegans. How many non-neuroscience, non-psychology people know who that is? Yeah.
You mean the C. elegans?
No, this person. You recognize the C. elegans? You know who that is? Okay, who knows who this is? Anyone from any discipline? This is Eric Kendall when he was younger, yeah.
Although he worked on aplesia, not C. elegans.
What's that?
His Nobel Prize winning work was in aplesia, not C. elegans.
But he did work with C. elegans in his lab.
But the
Yeah.
serotonin, 5 puffs of serotonin and reinforcement learning was in aplesia.
That's fair, that's fair. Yeah. Oh, I thought that was a hand.
Question about the previous slide. So when you were talking about, or this equation for learning with the alpha and gamma and so forth, is it in some sense universal? That is it like a linear approximation to any kind of learning scheme, or it's a bit like by analogy with like PID controllers. A PID controller is a linearization of an arbitrary controller, basically.
Mm-hmm.
So is this like a general linear version of
something else?
Any kind of a learning system or some sufficiently general learning system?
I don't like to think of it as too general, but it does appear in a lot of different types of learning, even outside of the paradigm of reinforcement learning. But I'm not sure exactly what I would commit to if I said a yes, so I'm going to say a rain check on that. What I would say is that this is a very 1990s idea of prediction error. Right now, things are a lot more complex. We have a lot of more complexities about different types of prediction error, dopamine neurons. And so this is like a basic version. Let's assume there's more advanced versions of this right now. Okay, now architecture. This is one of the most cited, I guess, architectures in reinforcement learning that appears in that early work in 1983 by Sutton and Bartow. So all they do here is that imagine that you have an actor and the actor just has to come up with a policy. Policy just simply means a sequence of actions. What are actions? If you have a grid world, actions could be up, down, left, right, and policy would be right, 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 left, 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 right, for instance. And the question is this the shortest path to reward from a starting location? That would be the optimal policy. We'll come back to it again. But the actor here, bless you, uses basically, the agent interacts with the environment and takes some action. The actor proposes an action. The action acts on the environment sends some reward signal. The reward signal is caught by something that is called the critique. And the critic just gets the, what did I do? What happened? Okay. And the critic just takes this reward, computes a TD error based on a value function, and sends that back so that the actor can kind of figure out what to do. So this leads to a law of effect for the actor that is kind of doing the policy, and reinforcement signal that comes from this critic who is using TD reward prediction error in order to send a kind of a TD error to the actor. So the actor-critic architecture is one of the most kind of basic algorithms of reinforcement learning that has been very prolific in neuroscience, in fact, especially for those who work in basal ganglia, in animal studies especially. So if you look at some of the works of Yael Niff, for instance, she has collaborated with many different neuroscientists on this idea. Okay, and also there are versions of this that you would see in very fancy algorithms that comes out of DeepMind. Still, to this day, this simple architecture, but more fancy versions of it, remains very powerful, this idea of actor-critic. Okay, so let's summarize what we just talked about. So reinforcement learning is, in this classic notion, is a paradigm where there is an agent and given a task or goal in an environment, learns a sequence of actions, which we call policy, to maximize expected value. What we mean by expected value, we mean discounted, that was the gamma, cumulative reward over future states. And that gamma determines how far into the future you take into account when you're trying to figure out the value of this. If I have a small gamma, I might consider what I will eat after IPAM. If I have a large gamma, I will consider how much coming here will influence my life in a longer scale. You see, so you can think about how much you will consider the future states depending on the gamma that you have, for instance. Now, actions, like I said, this is what we call a grid world. Actions could be left, right, up, down. Policy, sequence of actions, and options are abstract policy. So if I say generally, I have a different number or a different set of policies that can go from, I can have a set of policies that can take me from this corner to this other corner of the 4 rooms domain, another very famous and classic environment for doing these experiments. The set of all of those policies, this abstract notion of the idea that I can get from here to there, is an option. And then if you get you basically do an eigen decomposition of your option, you get eigen options. And the dream or the hope is that in a given environment, any policy would be a linear combination of the eigen options in that environment. I'm not going to go into details of that, but definitely can talk about it afterwards. Okay, reinforcement learning, again, is one where the agent takes actions to maximize expected reward. Some RL algorithms also learn representations and plan to achieve goals, and we'll talk about them shortly. So far, we only saw cached value for a state and action, right? So we only saw that memory aspect of it. Behaviorally and neurally, it has some plausibility. There is evidence from dopamine. There is evidence from predictive representations that we will look at hopefully soon. And it enables abstraction, hierarchy, generalization, and transfer in different ways. So that's why reinforcement learning has kind of survived even right now. Right now we are in an RL winter due to transformers. The 2010s were the RL kind of spring, I guess, because of the famous deep RL work that resurfaced these notions at DeepMind, combining connectionism and reinforcement learning to have deep RL. But one of the ideas that we were talking with David Silver actually was that right now, because we are in the RL winter, is the best time for innovation, because there is not like a requirement to keep up with anything really. So if you want to innovate in this area by thinking deeply and taking your time and then proposing one good idea, Reinforcement Learning Conference is also a good place to submit your work. There we really care about also rewarding innovative ideas and breaking with tradition. Okay, so right now we talked about varieties of reinforcement learning that had to do with rewards and the notion of value. So I'm going to ask again, who recognizes the shape of this matrix, or the shape of this maze and what it might? Can anyone guess whose face might come up after seeing this maze? Okay.
Oh, Shannon?
No.
Moriarty.
The band or the fictional character? Good band.
Isn't the Westworld, it's the Westworld symbol.
No, it's not. So we have Edward Tolman. But very good point of that whole series being very much inspired by behaviorism and how far you could take it. So against Watson and Skinner's behaviorism, we have Edward Tolman, who if you actually, it's interesting because when you look at the politics of these people and ideologies, they actually go well with the kind of scientific ideas they propose. Edward Tolman, who was at UC Berkeley, proposed cognitive maps. He has this obviously famous paper called Cognitive Maps in Rats and Men in 1948. That paper is a piece of art. If you read it, it's so well written. It's a review of 20 years of work that leads to that moment. In that paper, he's acknowledging work by people outside Berkeley that has not been even published. And some of them, I think they never got published, but he includes it in that paper, and that's why that work is very well known. He basically looks at the different types of experiments that go against this idea that you can only learn, an animal can only learn with reinforcement and there is no internal life. So Tolman talks about cognitive maps because he's interested in internal life and what's inside our heads. His idea was that to capture learning, the latent structure of the environment and having an internal model of the world is kind of at the foundation or at the heart of cognition in rodents and in humans. For his kind of learning, reinforcement is not necessarily required. And his classic latent learning experiment in the Tolman maze, to mention what the maze refers to, went against the behaviorist dogma of the time. How many people know latent learning? Okay, all right, let's go with it. So imagine there is a maze, and you drop a rat in a maze, and at the end of the maze, there is reward. According to behaviorism, the rat is learning what's going on because there is reinforcement, right? It will learn some policy. Now, imagine another group of rats. You throw them in the same maze with no rewards at the end. Will they learn anything? How will we know? What if we introduce reward after day 7? Will they learn the path to that reward faster? If they learn it faster than the first group, what does it mean? It means they learned something when they were not being reinforced about the map or structure of the environment. Does the logic make sense to people? Yeah.
It assumes that you're the only one able to give a reward. Maybe there's other rewards in the environment that are more intrinsic to being a mouse. Like, I don't like running into
We're
walls.
talking about external reinforcement.
I know.
In this maze, there is no external reinforcement for group 2. We're comparing group 1 and group 2 as natural scientists. In group 1, there is reinforcement. In group 2, there is no reinforcement at the end of the maze.
Curiosity doesn't count.
It's not, remember, behaviorism says external reward. It talks about what is in the environment. Yes?
I mean, okay, but when you say external reward, I mean, I agree with you because there could be reward just in the sense of like the pleasure of exploring.
Wait. We're talking about being against behaviorism. What does behaviorism say? It's only from the environment.
So what does that mean? Yeah, I guess I'm not sure I understand the distinction here between it.
The distinction is if you're saying the joy of curiosity, the pleasure of search, that is not an external thing in the world. That's internal notion of
But
reward.
the pleasure of cheese is. I mean, I'm not sure why.
Cheese is something outside of you that you are consuming. The pleasure that you derive from cheese is a pleasure from something external to yourself. It's very simple.
Pleasure of getting out.
Say again.
pleasure of getting out of the maze?
That is good. That is good. But they are kept for a particular amount of time in it. So it's not that they can it's not that they can get out. There are particular training regimen that they were kept there for a particular amount of time.
Okay, but there is no food in the maze. You need food, so you get out.
That's true. But they are kept again with the same amount of time there.
Well, to put,
And the location of the reward, they don't know where it's going to be. It's not at the end as in the exit of the maze, right? So the location of the reward can be dropped in any kind of place. But later on, at the time, they don't know. So, and this is not a maze that if they get out, then they get food outside of it. So, yeah.
I was just wondering, so between these three scientists, how did they define internal versus external rewards? Like, because I don't know, I'm still a little struggling sometimes.
Again, if you consume something in the environment, they call that external reinforcement. If something in the environment harms you, it's punishment. That is the way, the very simple way that
My
they.
experience, though, I guess, is to some extent, like, so I experience eating cheese, so is that the same as the cheese itself? I
If
guess
you
that's
do
the
not
question.
eat anything, you will die. So it's not just the kind of the psychological experience of it. It's actually required, and that's a very key and important thing. It's actually something that is related to your survival.
Right, okay.
And so rats are kept hungry. This is okay. I see that you're
So
nodding. You see what's
if I
happening.
need it to survive, it's like a kind of base instinct, whether it's more of a choice, it's kind of like an internal thing. Is that kind of the, you know,
Behaviorism is only interested in the external reinforcement, and that's important. That's the whole point of the contention between Tolman, who actually still considered himself a kind of a revised version of behaviorism, because at the time, behaviorism was interchangeable with the notion of psychology to some extent. But later on, you can see that, like, from this perspective that we are looking now, what was classical behaviorism that he was against is called behaviorism. So what people mean by now when they say behaviorism, they mean that classical extreme version.
okay.
Yeah.
So just to get an understanding, because I'm also struggling with this. So you're saying that the reward here is not that they enjoy eating the cheese, like because of the affection,
It's survival.
because the cheese actually helps them live another day. That's
Right.
the only form of reward that they're okay.
At least in the behaviorist experiments, they they use liquid and food. They use basically things that are like that. And usually you would keep the animal hungry so that it has motivation to do that. Also, Erica is our expert in animal behavior, so if I'm saying something wrong, please correct me.
Well, I thought you were going to say wait and direct all your questions to him.
I wanted to say that.
Get them out of the way now.
You can ask Erica more about animal behavior. All right, let's spend like 1 more minute maximum, and then we move on. Yeah.
well, I'm just thinking, to put it another way, I mean, the pain of repeatedly banging into the walls of the maze.
Yeah.
I mean, wouldn't that be an external punishment?
Have you, like, rodents are not blind. They don't necessarily back to the walls.
I mean, you're
They have a
thwarted a lot. I mean,
very particular vestibular system. They're very good at navigating different areas, you know. Yeah.
I mean, here's a thought experiment. Imagine you have a rat in the maze, and then, with some probability, find something that is edible or not.
There is none in the second
Well,
condition.
I know,
No, but let's
just experiment.
because we need to move on with regards to time. I don't want to do, but go on.
I'm just trying to say that there is an interpolation between a situation of Tolman and a situation with an exact reward.
Okay,
and
great.
In real life, probably conditioned the rat to always look and always remember the pattern, right? So
Behaviorism would disagree with you. Because for them, the rat would only learn if it has external reinforcement.
But how
that
does it know
long
it's in
period-
a maze as opposed to a general situation? It's always in a maze, right? This is a particular instance of it exploring its environment, right? So it learned that in any environment.
Take that with the behaviorists, please. Tell them that this is another way of thinking that this is a problem. Or are you saying this in defense of behaviorism?
I'm saying it in defense of them because
Okay.
I'm saying it just always does that because always there's some potential for reward, and so it learned to explore and always look for reward.
I see. So there is no difference when somebody actually gives you a reward versus they don't.
No, there's no difference whether you're in the maze or anywhere else because you're always looking for food.
So you're saying that even without external reinforcement, you will learn because you have some idea of reward. That they would disagree with.
You would say that you're always looking for food, and therefore, since you've been before oftentimes rewarded for looking for food, you've learned to look for food.
You are
This is a
abstracting to
particular-
some algorithm of learning that is inside your head that has been reinforced, and that is an internal algorithm. It's not the same as behaviorism that says it's all conditioning. You're talking about conditioning of an internal algorithm, which makes sense for people who have an internal life, not for those that don't have an internal life. So what you're saying is, I have an algorithm of search in general. That algorithm has been rewarded. Therefore, I'm running that algorithm all the time. Behaviorists do not agree with that.
Between a maze and a room. It's just,
But do you hear what I'm saying? I want to make sure that you're hearing what I'm saying. Good, okay. Okay, so 30 years after that seminal paper by Tolman, what do we have? We have John O'Keefe discovering what he called place cells. How many people have heard what place cells are? How many people have not heard what place cells are? Thank you for your honesty. So imagine that you have electrodes inside my hippocampus that are recording individual neurons. When I walk around here, bzz, every time I pass by this location, there's a neuron bzz, that is going to basically fire. That neuron, and I'm going to move around. This is the trajectory of me moving around. Bzz, and every time I'm there, this is going to be that kind of neuron that is firing, right? And then 30 years after that, you have the Mosers, who identify a grid field, which is this hexagonal structure, like a tiling of the space. And every time that you're in any of those tiles, all of that particular tiling gets activated. And that one is in the entorhinal cortex. Together, this grid fields and place fields form what in 2014 the Nobel Prize called the GPS of the brain. There's a lot of kind of complexities to this story. A lot of people in the neuroscience field are like, but this, but that, this is like, and those are all valid points. But this is just the general picture that I want you guys to know. So if you think about the idea of cognitive maps, this gives us some neural basis for learning representations or some kind of a map of the environment that is beyond just conditioning. According to like extreme behaviorism, you just have conditioning, but all of a sudden you have things that are standing for things, for locations in the world, regardless of whether they are rewarded or not at all. And so this idea is very much connected to Tolman's initial kind of revolution against behaviorism. And this was what basically inspired my own work, where I was interested in how memory is structured so that it enables both remembering, predicting, and planning. Why do I all of a sudden talk about memory? I mentioned hippocampus. Why? For those who are not familiar with natural sciences, why do you think I'm thinking immediately about memory when I was talking about place cells and grid cells? Because the medial entorhinal cortex, where the hippocampus and the entorhinal cortex are, is very foundational to memory. How many people have not heard of the patient HM? Patient HM lost his hippocampus. He could not learn new paths. He could not learn new things. He could not form long-term memories. But he remembered things very well from the past. And the entire field of studying memory and its relationship to hippocampus is very much indebted to HM allowing to be studied so widely. The interesting aspect about memory is when you are not like HM and you can learn new paths, you are capable of predicting or planning a sequence of actions that will get you from A to B based on this new path that you are learning. If you cannot learn that model of the environment, if you cannot learn that map of the environment, if you don't have your hippocampus, it seems like you can't. And I think that's quite important. Again, remember, reinforcement learning was about search plus memory. And it seems like it is not just activating where you are and helping you form a map, but also remembering that map that is important. Think about situations where you fly from somewhere to other. For instance, when I fly from New York City to Tehran where I was born, I can think about this plan at a very high level, or I'm going to fly to Tehran. I can think about it in terms of how I'm going to get to the airport, how I'm going to get from airport to my dad's house. Or I can think about very detailed steps. Cognitive maps that we use, these predictive representations that we use are multi-scale. And that is something that I hope that we will have time to show you as well. But in order to understand that, one question is, okay, there are these place fields and grid fields. There's some kind of a cognitive map that is remembered based on how they got activated during a particular navigation of a new building I'm in. But what do those learned cognitive maps look like? Are they storing one-step associations between, oh, I went left, and I got here? Is that like state, action, state tuples? State, action, next state, I guess, state 1, action, state 2 tuples. Those are the ways in which model-based reinforcement learning stores representations of the environment, and we will talk about it a little bit more. And then when you have that one-step association map, what you need to do at the moment of decision-making is what we call in model-based reinforcement learning, unroll all of these paths, and then compute the value at the end of all of them, compare all of that, and choose one of them. What's the problem if a biological creature does that? You might not make it. A lion might eat you while you're contemplating all the possible paths. So there are many kind of challenges. An alternative that was proposed by Peter Dayan, a computational neuroscientist in 1993. As you can see, the 90s was a very prolific time and a lot of things that you see, including the transformer architecture, have their roots in the 90s. Predictive multi-step maps might be built. And we will talk a little bit about that as well, where you have some kind of a compression of a multiple steps, depending on, again, another notion of gamma. So we had gamma for value, but this one is gamma for multi-step associations. And what you have here is a kind of compression that allows you to jump over a number of steps and figure out, okay, there is a path from here to there. And then you can go back and forth in this hierarchy of multi-scale representations to figure out then if you want to use the detail or if you're just planning generally. So when I'm trying to plan my flight from New York City to Tehran, I am not planning at the level of steps. But if I am planning to, let's say, I don't know, make sure that I don't run into the podium while I'm talking to you guys, that is at the level of steps. These are at very different scales that we are talking about. And in order to allow for easily using those scales, remember search plus memory, maybe sometimes we need to cache the results of a multi-step search. And that's the idea of the successor representation that has predictive representations. We will talk about it in detail, yeah.
When you're doing something like CS with trees, you generally want to structure a tree somehow, right? It seems to me like you're thinking about planning as a form of tree and trying to find a route from the root to the leaf or node which is most efficient. Are those ideas similar to people? I mean, almost like sounds like trying to do branch and bound kind of thing on a tree.
So not all MDPs or Markov decision processes are trees, one. And second, what you're describing is the main topic of hierarchical reinforcement learning. And eigenoptions are actually one of the approaches that are helpful for that. And I'll talk a little bit about the successor representation that compresses certain things is also helpful for finding out some of the sub-goals or kind of parts of a particular environment. If you are familiar with graph theory, and we will get into it more, but the successor representation is equivalent to the inverse of the graph Laplacian. So to some extent, so that's used for clustering your graphs. So your idea is basically, wouldn't it be helpful to cluster whatever graph it is that you're using? And that is a topic of hierarchical RL and also other algorithms. Okay, how do we compare these biological algorithms that we will talk about? I didn't talk about it in detail. We'll get a little bit more in detail. Between biological and artificial agents. The first step is we need tasks. Remember, Jacob really highlighted the importance of tasks. You need a task that your different alternative hypotheses or alternative models will behave differently on. And then you can have that task performed by your biological system of interest. Let's say a human, a rodent, a C. elegans, Drosophila, whatever animal it is that you desire to study. And then you can then compare which of your algorithm's behaviors look more like the human behavior. You can do this by fitting. I personally prefer normative approaches, which is you just see, can it generate similar asymmetries or shapes of behavior in general? And you will see what I mean by that soon. And then and that's the way that I would do. And I would also note that when I say behavior, I mean accuracy, I mean reaction time, I mean errors. If you have something that does two things at the same speed, but humans does one of them much slower, this is not a good model of human behavior. If you have something that is very accurate on one, but then you test two other tasks and it's extremely bad at it, that is not a good model of human behavior, which is why, for instance, transformers are not a good model of human behavior. once you have those models, you find your model that behaves more like humans, then you can look at the representations that model is using, look inside the brain, and say, am I finding similar representational patterns here? And then which brain region you're choosing will depend on how you think there is a potential similarity, again, the standing as, I guess, we go back to Jacob's talk, between those particular parts of your computational architecture and parts of the brain that you are studying. So if somebody says successor representation is a model of the hippocampus, that means that when I'm looking at those representations, I should find some kind of a similar structure of representations in the hippocampus. If someone says basal ganglia is a good is a good kind of like counterpart to the critic in actor-critic, then I should find some kind of signals there. So algorithmic and representational parts of the architecture, which parts of the brain do we want to hypothesize might be similar to, and then let's take a look at it. And you can use different methods. You can use direct recording, you can use fMRI. Some people even use pupil dilation as a measure of, or eye movements as a measure of neural activity, because, for instance, pupil dilation relates to locus coeruleus. So there's different ways that you can measure, and it doesn't necessarily need to be fancy or expensive. There are some simple ways to measure it too. This is some work that I have done, just to plug here if anybody wants to talk about any of these things, multi-scale predictive representations or cognitive maps that support memory and planning. And I will get to some of these aspects during this talk, but if you want to talk about these aspects, I would love to talk about it. Some aspects of it are at high level, but some aspects of it also apply to neural level. Another interesting thing, before I get to what it is that it's possible that this idea, just simple idea of having multi-scale predictive representation, could capture a general principle for memory organization. It captures certain behavioral and neural effects in statistical learning, in episodic memory, in context-dependent learning. I'll show some of them in clustering, as I mentioned, in response to the gentleman at the back. And also optimal sub-goal setting by clustering different rooms in this case. And it would be interesting to also talk about that. Like, can we find some general principles for organization or the shape of memory? Okay, so the first, yeah, what's, oh. Okay, so we talked about tasks. Jacob loves tasks. So let's take a look at a couple of tasks, as I promised, that we can compare the different models on, and then we can compare with behavior in humans and in rodents. You remember that I wanted to go to see my family. I actually went there in May for my sister's wedding. In order to make it there, I need to make sure that I'm adaptive and flexible when the rewards in the world change. If the coffee cart in the airport change, am I going to miss my flight? I'm sure it's happened to some people that they missed it because there was no coffee. Or the flight gate might change. Another thing that unfortunately happens a lot in New York City is that the subway lines run on each other. So A and F change their, run on each other's rails. So if that happens, am I capable of revising my plan? Am I flexible enough to be able to respond to all these things? The first is when the reward structure of the world can change. So somebody moves the cheese in them. It's not actually cheese, it's actually they give them chocolate. Rodents, they like chocolate more than cheese. Not unlike us, humans, mammalian roots. And then transition structure can change as well. If you think about a maze as a directed, in this case, undirected graph, then you can think about the change in a structure as, you pick a wall and then another path appears. That would be a change in the transition structure in the maze. Okay, let's go and take a look. Let's compare behavior between human and selected RL models and then figure out what those are. Oh, where is the task? Okay, I think I need to put the task here up first for you, just before we go. So let's say that the task is such that I'm in state 1 with probability of 1. If I take an action, I'll end up in 3, and from 3 to 5, and I get no reward. And then I go from 2, I go to 4, and then 6, and I get $50. just to test if everybody's okay with this. If you want to maximize reward between 1 and 2, which starting state would you choose? Does anyone prefer 1? Good, okay. So let's see. Now, let's say that, let me find the one to give you the actual experiment before we do this. Okay, I apologize for this. Okay, so let's say this was the task. Sorry, the numbers changed. And I asked you and you said 2. And then I drop you in phase 2, and you no longer enter 1 or 2. So I'm just dropping you into state 3, and I'm dropping you into state 4. It's very easy with doing experiments. And then you notice that the rewards have kind of changed. So you update the idea that you had of reward for location 5 and 6 and for location 3 and 4. But between 1 and so when I drop you in phase 3, you need to integrate something you learned in state 1 about, in phase 1 about state 1 leading to 3 and 2 leading to 4, and something you learned about the rest of these trajectories and what reward they lead to. You have to integrate that to tell me in phase 3, if I ask you, do you prefer 1 or 2, which one do you prefer?
1.
2 now.
2.
2. Oh, yeah, that's my bad, because in the other one, it was reversed. Okay, so this is reward revaluation. This is retrospective revaluation of reward. Remember, model-free reinforcement learning caches the value when it experiences going from somewhere to somewhere else. Do you think model-free can solve this problem accurately when it comes here? Who says no? Who says yes? No is correct because it didn't go back to 1 to change the cached value. And it has an expired idea of the world. Its idea of the world is outdated, not unlike, many people. And I don't know why I said that, just to be funny. Okay. It was not a mention of anyone, it's just like, okay, so model-free RL, who has no map of the world, just caches the value, cumulative value that is expected. Remember, this was the prediction error, the learning rate, discount parameter, etc. Only caches expected value, no map. It's very fast at decision time because all it has is what we call a lookup table. It's like, okay, V, A, and S. Okay, this is what I'm going to do. This one is the more valuable one. It can't reevaluate if the rewards change, if the maps partially change. Okay, we talked about model-based RL. Model-based RL stores, as I mentioned, a tuple of, hey, I have a probability map of ending up in state S prime given I started in state S and took action A. You have all of those tuples. You have a map of the world, has no rewards in it. And then you have separately a reward vector that says, here's the reward of being in state S and taking action A. Separate, right? So this is a time where we are a little bit more Tolmanian. We have separated rewards and maps of the world. And if I wanted to turn it into a matrix, that probability tuple into a matrix, this is what it would look like, right? I only know in this tuple about one-step actions. I don't know about multi-step things. So how would you figure out whether 1 or 2 is the better option? Any word somebody wants to throw at me?
Square the matrix.
Iteration. So iteration is the word I was hoping somebody would throw at me. Where you say, okay, from 1 I go to 3, then from 3 I go to 5, and then you can see, okay, and this is the value. And basically this is the Bellman equation way of computing it. How do we do that? V star would be the optimal value, meaning this is the best you can do. Max A is like only choose actions that maximize value at any given time. Like let's assume that you can do that. And then after that, at any given time, it's like, what is the reward that I observed when I was in state S and took this best action possible, plus the sum of every state that would be following this, such that based on me taking actions that maximize my value, and their discounted future but optimal value, right? And so every time that I have arrived to a state, what was the best value that I could get out of it? And then if you go back to the state that I am, if I iterate over all the steps that I go, and every time, as you can see, you're going to have another gamma here, how will I compute this sum, this iterative sum? Another possibility, like I mentioned earlier, is a successor representation, where you again store a map of the environment and the vector of rewards. The map of the environment is a multi-step map, and I will get in a second into what it looks like. Let's just say that, first of all, it's not a probability. It is expected future occupation, which is how often, on average, do I expect to visit a particular location given I start from a certain point. So let's say from the entrance here, how often do I expect to visit my office? How often do I expect to visit Erica's office? How often do I expect to visit the bathroom? All of those are expected future occupations. And then you have a very nice linear combination of them at the moment of decision that gives you the value. It's cheap, it's fast, and it's flexible, because if I move the cheese or chocolate or the reward, as you can see, I have only changed this vector, not the map. And as long as I have only learned that one-step thing, which is just, oh, in this location, I got this much reward, and I update this, the value should, at the moment of value computation, I should be very easily capable of combining the map that I had with the new vector of rewards. Does that make sense to everyone? Yes? Okay, good. If I unrolled this matrix if I turned the successor representation into a matrix, we see some nice properties of this matrix. And this is why I usually name the talks that I give about this research the shape of memory. Here, your rows are giving you what comes next, or the successors. And your columns give you what came before, or predecessors, which is, in temporal terms, known as the past and the future. So you have one structure now. So it could be non-temporal. So we have one structure now that is learned simply, and it's a map that is not just a one-step map, and it gives me both the past and the future. So it's a predictive representation, a predictive structure for memory. Some fun thing, do you remember that temporal difference learning of value that we saw earlier? Instead of updating value, you can update the rows of the successor representation here. And instead of adding the observed reward, you can add a one-hot every time you observe the next state, which is S prime. And by the way, I'm realizing the person who asked the question about S prime might have been thinking about derivatives. And I think maybe that's why they asked. No? OK. I see. Got it. So people can see how this relates to the temporal difference learning, right? Do you guys remember what that one looked like? We had here reward, and we had here V instead of M. And V was one particular value that you were going to cache. In this case, M is a row for your S. It's the row of its successor. There's something very fun that happens here. What do you see here? If anybody wanted to tell me this in an intuitive way, this gamma, the row of the successor representations of the next state that you observed, basically means you are inheriting the future of the new state that you went into. So when I come to IPAM, I inherit the future of the museum, if I go there. Or I inherit the future of the jail, which I hope never happens. And so you don't necessarily just talk about the particular value of the future state, but where it's going to lead you. Does that make sense? And this is why gradually, as you move around the world, you start to have different futures associated with a given state based on many different things that you've learned over time.
Sorry,
Oh, yeah.
Just about something. So if you look at your tree picture, right, which has many, many, many outcomes, wouldn't this mean that this matrix M would have to be humongous because it has to account for all the different endpoints of your tree?
It depends what your scale is, because this gamma determines how far are you seeing things. So if the gamma is small, you might only have it until a couple of steps ahead, basically.
Because, I mean,
Yeah.
taking them essentially.
Yeah.
So
And then, and then you're getting to a very fun part, which is why the brain is multi-scale. Because then the thing that a higher gamma part of the brain sees is not those individual steps. It sees that kind of bigger steps, right? So this is how you can build multi-scale predictive representations. Hopefully we will get to it. I think there's some fun mathematical things that have not been done that can be done here, so I'd like you to stay with the question that you have so that we can maybe iterate over it soon.
Sorry, can I just ask
Yeah.
one clarifying question about the PD learning analog? So this is saying if I'm updating the row for state S when I succeed it with state S prime.
Yes.
Okay.
Exactly. And also, this is a successor prediction error. If you have been here long enough, this would be 0 because you're like, oh, I know this already. I've been to IPAM. I know that I'm going to end up in the museum. So this would be the equivalent of that prediction error that I mentioned, but it's not dopamine prediction error or value prediction error. This is a successor prediction error, which could be 0, could be non-zero, right? If the world is stationary, at some point this will be 0. When the world is non-stationary, this should always kind of change a little bit. And so when I say one hot, by the way, I just mean that there is a vector and then there is 1 for the location of S prime and 0 everywhere else. That's all I mean. Okay, so let's look at them side by side. That was the one-step model-based approach, and it uses the Bellman equation iteration in order to compute value. And this one is the cached multi-step discounted future or expected occupancy from every row state to every column state. And this is the kind of the linear combination. And you notice I have pi and gamma. How many people don't know what pi is? Pi stands for policy simply, because the successor representation is learned in a policy-dependent way, which is actually not trivial, and we'll talk about it. But I'm excited to say that we can return to the neural kind of underpinnings of cognitive maps here, which is, it turns out that, first of all, the SR columns, they are a good model of place fields, in fact, which, in fact, are skewed towards the direction that you are more likely to go. This is for, if you see them that are symmetrical, that means that there was a random policy, meaning the rat was going in every direction or the rewards were dropped in random location. But if there is one part of the room and that is the only direction, then the place fields will start to be skewed towards that direction. And that does happen with SR as well, because your expected future occupancy for this path is going to be higher than, let's say, this path or that path. Yes?
Sorry, I'm confused about the eigenvector thing. I mean,
Yeah.
the eigenvector doesn't depend on gamma, right?
No.
Right? So then why is it not the same thing as just the eigenvector for the full Laplacian?
Well, we don't have the full Laplacian, but
I mean, but what you're
Yeah.
doing here is like,
But this
instead
is
of
in
the
the
Laplacian,
inter-
you're looking at like 1 plus gamma times the Laplacian inverse,
I minus
right?
gamma, so it's
I minus gamma Laplacian inverse, right?
So it's like
the
the
geometric series for 1 minus
I
gamma.
minus gamma t inverse would be the, basically this is if t is your one-step map, I minus gamma t inverse is an approximation of only, then this is the one that relates to the graph Laplacian. This is the approximation of only the random policy, not the policy-dependent one. You see, that's a very interesting question you asked. You're really pointing at the nice mathematical properties. And you know what? The grid fields also get skewed after a while. Slower, but they do. And you know, there is a lot of chicken and egg stories of like the relationship between grid and place cells. There's a lot of nice modeling to be done, but some that have been done, which are also things that we can talk about. And I'd love to talk about this one too, because here we used another thing associated with Laplace, which is we figured out that the inverse of the Laplace transform gives you the distance between cells if you take it over successor representations with different gammas. So the different gammas are also helping to figure out what is the distance between different things. And turns out when we figured it out mathematically, we were like, how are we going to test this? And then I just mentioned it to some friends, and they said, oh, there's a bat study in Israel, and you can just take Ulanovsky's results. It turns out that they found distance to goal cells in the bat, and then it was found in the rodent and in humans, so we could actually put it together as evidence of it. Any questions? Yes.
Sorry,
Wait. With regards to time, am I trespassing or?
You probably want to finish.
I want to wrap up. In how many minutes?
-2.
Okay, then let's go to questions. We can go to the next, yeah.
My question was really basic. I just wanted to, I was going to run past what this grid is showing again. I just didn't understand.
Oh, okay.
I can always do that offline if that's easier. I don't want to.
No, that's fine. If anybody else has this question, it's important. These are all the states in this experiment that I mentioned to you. State 1, 2, 3, 4, 5, 6. State 1, 2, 3, 4, 5, 6. And here's where you start. Here's when where you end up. If I start in 1, how often do I expect to end up in 2, 0, because they don't have a path to each other?
Does this, would this be if you unrolled it kind of indefinitely? So you took a definite number of steps, or after how many steps, I guess?
That's similar to the question that was asked earlier. It depends how far of the states, the parts, the algorithm you're talking about sees. It doesn't make sense to assume infinite states,
So
obviously.
this is why the two are different. One was showing 1, and this one is showing gamma because it's using a different horizon to check.
No, they were both having the same, they both have the same number of states here. Assuming the same number of states.
I meant the 1 versus the gamma. Is this why some of these are gamma squared? Like the left-hand side has just got the 1s on the diagonal, and the one on the right-hand side has got the gamma.
It's not the diagonal, but what do you think this one is?
I don't know. That's kind of what I was trying to say.
It's the probability of ending up in 3 if you take an action in 1. That's the probability. What is the relationship between 1 and 5 here?
You'll never go to 5 after
Why?
steps because it's got 0 there.
Then why is it not 0 there?
I don't know.
Because that's multi-step. Because this one captures multi-step dependencies. This one captures one-step dependencies.
Oh, okay.
Thank you for asking. That's actually very important.
Okay.
And that's why I put gamma here. And this gamma is not the probabilities. This is just, and that's why it's a different color than the rest. This means that this is intense. Let's go back here.
So actually, maybe the really confusing thing in this case is that in that case, whether you take 2, since you have nowhere to go after 5 or 6, then here the cube of the initial matrix is 0. So there's no difference between the 2-step matrix and the 3-step matrix.
There is, in the sense that here, I only do a one-step.
Where would you put gamma cube? There's no gamma cube.
I'm not sure what you mean by that, to be honest with you, but let me just clarify what I mean by what I'm saying. And what I mean is that when you're computing value, you do it in one step by combining a linear combination. In this one, you need to iterate. And you need to iterate 4 times and then compare the values.
No, but I'm just saying that, there isn't. So if you were to draw this matrix for 3 steps, allowing not just 2 steps but 3 steps,
there isn't no 3 steps in this matrix.
In this case, so it's insane.
It's a nilpotent matrix. So.
Why would I put a location for things that don't exist?
Well, what I'm saying is, if you had, say, a path from 5 back to 1 or something like this, right? Then
we could just then you will just have 5 to 1. That's
right, but then you would have also gamma cubed and a gamma fourth and so forth, right? Because you would be able to go in loops.
No.
3, 5 back to 1.
So I'm trying to understand what you're saying, but yeah.
Yeah, so if you expand out that expression, this m equals, you get 1 plus gamma t plus gamma
By the way,
squared.
this is By the way, this is only for random policy, not for policy.
But I mean, and it seems to me like you're just adding up these matrices here, and then the cubed 1 and higher is equal to 0. It's the 0 matrix, and that's why your matrix stops at gamma squared. Like the cube of your matrix is 0.
Why would I want it though?
No, I'm just saying that that's in fact what happens.
Okay.
In your particular example,
you
cannot take more than 2
example,
steps.
it is a fact.
But there is no more than 2 steps. That's what I'm trying to say.
But more generally, there'd be other higher order stuff. Right?
If you add from this location to here, for instance, and then from here back there, you might change, but it doesn't change by it would be 5 steps then. You need, I see what happened. Wait, no, that's what I did not maybe mention because I kind of assumed. I apologize. How many people are familiar with Markov decision processes or MDPs? Okay, in RL we assume MDPs, which means they have a terminal state or a finite. So they are, this is finite MDPs. So they will have a terminal state. So you don't fall into a infinite loop because of that. Okay, thank you for. I'm sorry that I didn't mention that. I think I'm making assumptions, and it will help me to add that to the talk. Yeah.
So why would there be a problem with an infinite loop if gamma is less than 1? Like you just get a convergent geometric series, right? Or
and for small enough gamma.
For reinforcement learning, at least the assumption is that there is an end. We do have particular special cases for open-ended learning where you can stay in the maze for your life and you have continual learning in it, right?
You allow
Then-
the loop, would it be forgetting stuff essentially?
Depends on your gamma, no. For instance, if I have a gamma that only goes 3 steps into the future, it would never even know that there is a loop because it doesn't care about it. If I have another matrix, what is the,
Oh,
yeah.
finish your sentence.
Oh, that's it. Like, is it clear-ish? Okay, I see nods from everybody who was concerned. I see someone who's shaking their head very concerned. What is happening? Is everything okay?
Well, I mean, I think that.
No.
Okay.
This is not an open-ended learning situation. We have a terminal state.
Oh!
Is now, if you have more questions, I'm sure I'm happy to get you some coffee, Ida. We'll stay there and answer questions. Let's thank Ida very much.